Okay, hello, we're back. I'm back to work. And we are going to do 8.5. So let me get my stuff here. Okay, we are doing 8.5. And 8.5 has to do with multiplying radicals, multiplying and dividing. So they're going to have stuff that looks like this. Okay, when multiplying, outsides with outsides, insides with insides, okay? That is the key to this whole assignment. Outsides with outsides, insides with insides, okay? This is a number that's on the outside. This is a number that's on the inside. So when I FOIL this, I can only multiply an outside number with an outside number, which in this case is 1, and an inside number with an inside number, which doesn't exist. So 7 times radical 5 is 7 radical 5. 7 times radical 2 is 7 radical 2. Now, negative radical 3 times positive radical 5 is going to be a negative, and they're both inside, so I can multiply them and get 15. And negative radical 3 times positive radical 2 is going to be a negative radical 6. Now, are there any like terms? Is there anything that can be combined here? No. Is there anything that can be simplified? Can any of the radicals be simplified? Nope. So this is your answer. Okay? Let's try another one. What if I had the square root of 10 plus the square root of 3 times the square root of 10 minus the square root of 3? All right? Remember, insides with insides, outsides with outsides. Okay? So, square root of 10 times the square root of 10 will be the square root of 100. You can multiply them. They're both radicals. Square root of 10. By the way, they both have to be the square roots too. If one was a square root, one was a cubed root, you couldn't multiply. They have to be the same type of radical. Square root of 10 times negative square root of 3 is negative square root of 30. Positive square root of 3 times square root of 10 is positive square root of 30. And positive square root of 3 times negative square root of 3 is negative square root of 9. Now I want you to look. Can I do anything with that? I sure can. The square root of 100 is 10. Can I do anything with these two? Are they like terms? We have negative 1 square root of 30 and positive 1 square root of 30. It's like a negative 1x and a positive 1x. They cancel out. Minus, what is the square root of 9? 3. So look what my answer is. Look at the difference between the first question I gave you and this one. Well, I want you to look at the difference between what was being multiplied. Each one of these things had nothing in common. But look at this. Remember from our factoring, this is the difference of two squares. Square root of 10 plus square root of 3, square root of 10 minus square root of 3. When you have two things that multiply out like the difference of two squares, you're going to get rid of the radicals and you're only going to have a number. And that's important to remember. These are actually, these two right here are called conjugate pairs because they cancel everything out. They're called conjugate pairs. All right? Now, that is not the same as this. The square root of 7 minus 3 squared is basically the square root of 7 minus 3 times the square root of 7 minus 3. You're multiplying the whole thing by itself. These are not conjugate pairs. One isn't plus and one isn't minus. They're both the same. So the square root of 7 times the square root of 7 is going to give me the square root of 49, insides with insides. The square root of 7 times negative 3 gives me negative 3 times the square root of 7. It's an outside and an inside. Negative 3 times the square root of 7 is another negative 3 square root of 7, outside and inside. And negative 3 times negative 3 is positive 9. Well, what is the square root of 49? 7. Are these like terms? Yes. What's negative 3 square root of 7 and negative 3 square root of 7? I mean negative 6 square root of 7. And we still have this plus 9. Are these like terms? Yes, they are. So my final answer is 16 minus 6 square root of 7, because 9 and 7 added together make 16. Okay? Now, that's the multiplying. Here's the dividing. Now, you can never have 0 in a denominator. Well, you also can never have a radical in the denominator, because the square root of 7 is what we call a non-repeating, non-terminating decimal. Okay? It's a non-repeating, non-terminating decimal. So we really have no idea how many pieces we're cutting that pie into. The square root of 7 is not an exact end complete number. It's a non-repeating, non-terminating decimal. So we cannot leave a radical in the denominator. You can have a radical in the numerator, but you can never have a radical in the denominator. Now, how do we get rid of it? Well, the best way to get rid of it is to multiply it by itself. Because if I multiply the square root of 7 times the square root of 7, I get the square root of 49, which now becomes 7, no more radical. But whatever you do to the bottom or denominator, you have to do to the top. And then basically, we're really only multiplying by 1. What is the square root of 7 over the square root of 7? 1. So we're not changing the value at all. We're multiplying it by 1. What we're doing, though, is getting rid of the radical or square root sign in the denominator. Outside and inside becomes 3 square root of 7. Inside and inside becomes 49. And what is the square root of 49? 7. Now, if outside numbers could reduce, we would reduce. You don't reduce inside numbers. That's inside, that's outside. Cannot do that. But if outside together numbers could be reduced, we would. In this case, they can't, so you just leave it. All right? What if I had 5 times the square root of 2 over the square root of 5? Can the 5 be there in the numerator? Yes. Can the square root of 2 be in the numerator? Yes. Can the square root of 5 be in the denominator? No. So we have to multiply the bottom, and whatever we do to the bottom, the top, by the square root of 5. Okay, outside, inside. I multiplied these two together, 5 square root of 10. And then that will be the square root of 25. Now, we know that the square root of 25 is 5, and these are outside numbers, so I can reduce. So my final answer is the square root of 10. All right, let's look at another one. Let me get a new board. Okay. What if I was given it this way? The opposite of 18 over 125. Well, we all know that's the opposite of the square root of 18 over the square root of 125. Now, we can multiply the bottom and the top by the square root of 125, but you're better off simplifying first. You're always better off simplifying first. And I want you to see that the square root of 18 can be 9 times 2, and the square root of 125 can be 25 times 5. Which means I get the square root of 9 times the square root of 2, over the square root of 25 times the square root of 5. I'm going to come down here, which means 3 square root of 2 over 5 square root of 5. All I did was simplify these. And there's your answer. Does 3 and 5 reduce? No. Does the square root of 2 have another square root of 2 to reduce? No. Does the square root of 5 have another square root of 5 to reduce? No. You cannot reduce inside radicals, only outside numbers. All right, what if I had negative 6 over the square root of 12? Oh, and I forgot, all of this is negative, sorry. Negative 6 over the square root of 12. Well, there's nothing I can do to negative 6, but I can reduce the square root of 12, because that is 4 times 3, which means it's negative 6 over the square root of 4 times the square root of 3, which means it's negative 6 over 2 square root of 3. Now, the 2 can become a 1 and the 6 can become a 3. So really, I have negative 3 over the square root of 3. Can I reduce an outside with an inside? No. So now I'm ready to get rid of the radical in the denominator by multiplying it by itself, which gives me negative 3 times the square root of 3 over the square root of 9. And what is the square root of 9? 3. Can these reduce? Yes. So I get negative 1 or just negative square root of 3. Okay. Look at another one. What if I had the square root of 50 m to the 4th over p to the 5th? Well, that's the square root of 50 m to the 4th over the square root of p to the 5th, which for 50, I can say 25 times 2, that's a perfect square, and m to the 4th is a perfect square. For p to the 5th, I could say p to the 4th times p. What I'm doing is simplifying first before I reduce. All right, what is the square root of 25? 5. What is the square root of m to the 4th? Remember, you take 2, divide it into 4, and you get 2. And what's left over? Square root of 2. Again, what's the square root of p to the 4th? P squared with the square root of p left over. Now let me rewrite this. We have reduced it, but we're not done because there is still a radical or square root sign in the denominator. So I need to multiply by itself to get rid of it. And remember, outsides with outsides, insides with insides. So 2 and p gives you 2p. This gives me p squared times the square root of p squared. What is the square root of p squared? P. And then what can I do with this? This becomes p to the 3rd, because you need to combine like terms. And there's your answer. All right. What if I had the cubed root of 27 over 16? I would simplify it. What is the cubed root of 27? 3. Square or cubed root of 16? No. But there is a perfect cube inside. So I get 3. What is the cubed root of 8? 2, with the cubed root of 2 left over. Now, when it's square root, we can multiply it by itself and get rid of it. If I multiply the cubed root of 2 times the cubed root of 2, I'd have the cubed root of 4. And that's not a perfect cube. What do I have to multiply 2 by to get it to be a perfect cube? I would have to multiply it by 4, because then I get 8. And the cubed root of 8 is 2. Whatever I do to the bottom, I have to do to the top. So I get 3 with the cubed root of 4 on top, and I get 2 with the cubed root of 8 on the bottom. What is the cubed root of 8? 2. And what is 2 times 2? 4. Does 3 and 4 reduce? No. Can you reduce insides with outsides? No. So that's as far as you go. That's your answer. Okay. Now, one last thing in this section, and that has to do with something that looks like this. Okay, now in the denominator, we have two pieces being added or subtracted, in this case added. You can't just multiply by the square root of 2 to get rid of it, because then if you multiplied all of this by the square root of 2, that would say the square root of 4, fine, but then you get square root of 2 again. So that's not what happens. Do you remember how when we looked, if you look back on what we've already done, when we multiplied something by its conjugate pair, remember I told you it was called the difference of two squares? There was no more radicals, it was just a number. I think the answer was 7. That's what you have to do when you get to have problems like this. You multiply it by its conjugate pair. Multiply it by its conjugate pair. Now, my best advice to you is in the top, do not multiply, because you want to know if you can reduce it all. So don't multiply. Don't FOIL it out, because then you'd have to take it back out. You'd have to factor it back out to see if it reduces. So just write it like that. Bottom, though, we have to multiply. 1 times 1 is 1. 1 times negative square root of 2 is negative square root of 2. Square root of 2 times 1 is positive square root of 2. And square root of 2 times negative square root of 2 is negative square root of 4. Which gives me, again, this over. What happens to these? Cancels out. So I have 1 minus, what's the square root of 4? 2. I have negative 1. Which means I can leave it like this, or I can just put the negative up here and get rid of anything on the bottom, the 1 on the bottom. Either way, and that's your answer. All right, let's try a couple more like that. Let's try a couple more like that. What if I had square root of 2 minus the square root of 3 over the square root of 5 plus the square root of 3. Okay, what am I going to have to multiply it by? I'm going to have to multiply it by the square root of 5 minus the square root of 3. Square root of 5 minus square root of 3. All right, let's do the bottom and see what happens. Square root of 5 times square root of 5 is the square root of 25. Square root of 5 times negative square root of 3 is negative square root of 15. Square root of 3 times the square root of 5 is positive square root of 15. Square root of 3 minus the square times negative square root of 3 is negative square root of 9. Which means I get 5, so the square root of 25, those cancel out, minus 3, which is 2. And on the top, I have the square root of 2 minus the square root of 3 times the square root of 5 minus the square root of 3. Now, because this is not just a single number multiplied by all this, they're going to want us to multiply this out. Square root of 2 times square root of 5 is the square root of 10. Square root of 2 times negative square root of 3 is negative square root of 6. Negative 3 times that, negative square root of 5 is negative square root of 15. And negative 3, square root of 3 times negative square root of 3 is positive square root of 9, which, go down over here, gives me the square root of 10 minus the square root of 6, minus the square root of 15 plus 3 over 2. And that's as far as you can go. That one was kind of ugly. All right. What if I had this? 6 plus 2 square root of 5 over 4. I can have that. 4 is in the denominator. There's no square root in the denominator. It's fine. What they want you to see is whole number, number outside, and number on the bottom. If you can reduce all 3, you can reduce it. Can we reduce all 3? Yes, we can. what goes into 6, 2, and 4? 2. That becomes a 1, that becomes a 2, and that becomes a 3. So you had 3 plus the square root of 5 over 2. Now let me show you an example where it's not. Okay, here, what's outside here and what's here? Do they all three have something we can reduce by? No. Look at this. Can this be reduced? Can the square root of 8y squared be reduced? Let's come up here. The square root of 8y squared can be the square root of 4 times 2 times y squared. And what is the square root of 4? 2. What's the square root of y squared? Y. And then you have this left over. So we can rewrite this as 5y minus, what did I just get? 2y times the square root of 2 over 6y. Now look at all three pieces. What can be reduced? The y. So you're left with 5 minus 2 times the square root of 2 over 6. And that's your answer. All right, that is 8.6. No, sorry, that was 8.5. All right, we're going to do 8.6 as well. We can get that one done in here. All righty. Go to 8.6, okay? 8.6 is solving equations with radicals. Remember, radicals are just square roots, cube roots, whatever. It's the thing with the little house. Okay? If I had x squared equals, no, sorry. If I had the square root of x equals 5, you've seen that if you multiply a radical by itself, the radical disappears. So there's something called a power rule. Okay? The power rule says you can square to get rid of the radical, but whatever you do to one side, you have to do to the other. So the square root of x squared drops the radical and gives me x, and 5 squared is 25. And there's my answer, using what we call the power rule. Okay? So if I had the square root of y equals 2, I could square both sides and get y. Square root of y squared drops the radical, and 2 squared is 4. Okay? So we're going to do some rules here. First of all, in order to solve equations with radicals, you have to isolate the radical, meaning radical on one side, everything else on the other. Then you use the power rule to get rid of the radical. Then you solve and always check. It's important to check, and I'll show you why. If I had the square root of 3x plus 4 equals 8. All right, let's go through. Is the radical isolated? Is it on one side, everything else on the other? Yes. All right, so now I can apply the power rule. I can take this radical and square it, and whatever I do to one side, I do to the other. Now, just like when I had the square root of x and I squared it and it just became x, when you square a radical, a square root, it drops it and you just have what's inside. But here, 8 squared is 64. All right, now we solve for x. 3x equals 60. Divide by 3, x is 20. And go back and check. Put in the 20 here. 3 times 20 is 60. That's 60 plus 60. 60 plus 4 equals 64. Is the square root of 64 8? Yes, it is. Okay? All right. 5x plus 1 equals 4. Is the radical on one side, everything else on the other? Yes. So I apply the power rule. It's a square root, So I square it. If it was the cubed root, guess what? You'd cube it. If it was the fourth root, you'd fourth it, etc. That's what they mean by the power rule. Okay? So now that drops the radical. I just get that, but 4 squared is 16. Now I solve for x by moving the 1 over and dividing by 5, and I get x is 3. If you put in a 3 here, 5 times 3 is 15, plus 1 is 16. Is the square root of 16 equal to 4? Yes, it is. So you have done well, and it is right. Okay, so then what would I do if it looked like this? 5x minus 1 plus 3 equals 0. Is the radical isolated? No, it's not. So I need to move the constant or number over so that it is isolated. Now I can apply the power rule. All right, that drops the radical, and negative 3 squared is 9. Now I solve for x by adding the 1 over. I get 5x equals 10, and I divide by 5, and I get x is 2. Now I need to check. Let's put it in here. 5 times 2 is 10, minus 1 is 9. The square root of 9 is 3. Does 3 plus 3 equal 0? Ooh, no. Okay, which means this doesn't work. This is not an answer, and this is the key right here. We moved that over and it became a negative. Will the square root of anything ever be a negative number unless there's a negative sign on the outside? So if you saw that in the beginning, you would have known, no solution. So you have to be careful, and you always have to check it, okay? All right, what if I had the square root of 4 minus x equals x plus 2? The square root, that's a 4. The square root of 4 minus x equals x plus 2. Is the radical isolated? Yes, it is. So we can apply the power rule, which means this drops and I get 4 minus x, but this is x plus 2 times x plus 2. So I have 4 minus x equals, I'm going to multiply all this out, x squared, 2x, 2x, and 4, which gives me x squared plus 4x plus 4. Now, if you remember from 095, we did stuff with x squared. Whenever you had a variable that was squared, you got everything on one side, 0 on the other, and you factored to solve. So I'm going to move this and this over. So I get 0 equals x squared plus 5x, and what does negative 4 and positive 4 equal? It's gone. Now, what's the first rule of factoring? What can I take out? And I can take out an x. Now, factoring means you take something that's being added or subtracted and change it into a multiplication problem. Do we have a multiplication problem now? This times this. So you set each piece or each multiple equal to 0 and solve. Uh-oh, where'd it go? Sorry. I get x equals negative 5 and x equals 0. Now, we have to see if those work. We have to see if both of those work. So put in a negative 5 here. You get 4 plus 5, which is 9. You got to put a negative 5 here. The square root of 9 is 3. Does 3 equal negative 5 plus 2? No, it doesn't. Okay, put in a 0. 4 minus 0 is 4. Square root of 4 is 2. 0 plus 2 is 2. Does 2 equal 2? Yep. So this answer doesn't work. This is the only answer that works. Okay. All right, let's try another one. Let's try the square root of, I'm just wrong here, x squared minus 4x plus 9 equals x minus 1. Is the radical isolated? Yes, it is. So we can apply the power rule, okay? So this just becomes x squared minus 4x plus 9, but this is x minus 1 times x minus 1, which means I have to multiply it all out. X times x is x squared, x times negative 1 is negative 1x, negative 1 times x is negative 1x, and negative 1 times negative 1 is positive 1. Okay? Combine like terms, you get x squared minus 4x plus 9 equals x squared minus 2x plus 1. I have an x squared. I need to get everything on one side, 0 on the other. But what happens when I move this over to the other side? Gone. I'm left with negative 4x plus 9 equals negative 2x plus 1. So now I just need to solve regular. Variables on one side, so I'm going to move the 2x over. I get negative 2x plus 9 equals 1. Move the 9 to this side. I get negative 2x equals negative 8. Divide by negative 2, and I get x is 4. Now we have to still go back to make sure it works. If I put in a 4 here, I get 4 minus 1, which is 3, and 3 squared is 9. Okay? If I put a 4 here, I get 16 minus 16 plus 9. So that's gone. I get the square root of 9, which is 3, and what is 3 squared? 9. So it works. It's a viable answer. All right, one more example. One more example would be cubed root. What if I had the cubed root of z plus 5 equals the cubed root of 2z minus 6? Well, there's two radicals here, but they're all by themselves on each side. So look what we can do. We can apply the power rule. That gives me z plus 5, and that gives me 2z minus 6. Just want you to see whatever the power is, you have to use the same, okay? Now you move the 2z over. You get negative z plus 5 equals negative 6. Subtract the 5. You get negative z equals negative 11. Divide by the negative 1, and you get z is 11. Okay? You go back and check that. You will find that 11 plus 5 is 16, cubed root of 16. 2 times 11 is 22, minus 6 is 16. So it works. You get this cubed root of 16 on both sides, so it works. All right, that is 8.5 and 8.6. All right, enjoy.